All right, let's just jump right into this explainer and completely shatter, totally bust, the absolute biggest misconception in construction, the idea that concrete needs to dry to get hard. Honestly, this fundamental misunderstanding costs the industry millions every single year in failed structures, crumbling surfaces, and completely unnecessary repairs. Today, we're diving deep into the actual science of concrete strength, how extreme environments destroy it, and the exact playbook you need to protect your pores. So to kick things off, we really need to rewire how we think about the hardening process. Look, while stuff like paint or regular glue hardens by drying out and losing moisture, concrete? It's a completely different animal. It actually needs water to undergo a continuous chemical reaction known as hydration, which means if your fresh concrete is drying, it's actively failing. Let me just repeat that because it's absolutely crucial. Drying is the enemy here. Curing is actually about trapping moisture in, letting those water molecules bond with the cement particles to create calcium silicate hydrate, or CSH gel. That gel, it is the literal microscopic glue holding the entire building together. And you can see the sheer catastrophic danger of moisture loss brilliantly illustrated right here when we look at the age versus compressive strength curve. See that line for properly cured concrete where the moisture is locked in? It steadily climbs right up to reach 100% of its design strength over 28 days. But wow, compare that to the neglected concrete that dried out way too fast. The chemical reaction literally just stops dead in its tracks. It permanently plateaus at roughly 50 to 70% of its potential strength. No matter how much rebar you threw in there or how perfect your mix was, if you let it dry, you've compromised the entire structure. To really wrap our heads around why this happens, we've got to zoom way in to the microscopic level. Deep inside that mix, during hydration, the cement particles are actively building two major things. First, literal microscopic bridges that connect the particles into a solid, heavy-duty load-bearing network. And second, dams that essentially block up the porous, water-filled pathways, which is what makes your concrete watertight and durable. So the big takeaway here is that without water, this CSH gel, that vital microscopic glue forming those bridges and dams, it simply stops forming, just completely stops. And without the bridges, well, you lose your structural strength. Without the dams, you're left with highly porous, super weak concrete that acts like a sponge for corrosive chemicals and moisture, which will eventually rust right through your internal steel reinforcement. Not good. Which brings us to the harsh, practical reality of hot weather site conditions. If you're pouring in extreme heat, like, say, in a Pakistani context during the dead of summer, working in ambient temperatures hitting or pushing past 95 degrees Fahrenheit puts your hydration process in immediate peril. Sure, high temps speed up the chemical reaction, but they also drastically and dangerously accelerate the evaporation of the exact water your concrete desperately needs to survive. Out there in those hot, dry, and usually windy conditions, you're up against a fatal mathematical equation right on the surface of your slab. As fresh concrete settles, the heavy aggregates sink down, pushing free water up to the surface. We call this bleeding, but when the hot environment evaporates that surface water faster than the settling concrete can bleed it up, disaster strikes. You enter a state of severe moisture deficit within hours, sometimes literally minutes. Now, what's really fascinating here is how the buildup of negative capillary pressure spikes as evaporation continues unchecked. When that evaporation equation flips on you, these invisible forces start tearing the concrete apart. As surface water vanishes, the water level drops way down into the microscopic spaces between the sand and cement particles, creating this massive, massive buildup of internal pressure. And here's exactly how that translates into structural failure. As the surface loses water, tiny curved water surfaces, called menisci, form between the solid particles. Think of them like microscopic rubber bands. As they dry, they pull the solid particles closer and closer together, physically shrinking the surface volume. But the concrete underneath hasn't shrunk yet, so eventually these microscopic rubber bands pull so hard that the tensile capacity of that young, weak concrete is completely exceeded, and it literally rips itself apart. We call this plastic shrinkage cracking. Okay, let's pull back from the microscope for a second and visualize what this actually looks like on an active job site. Because the difference between total success and structural failure often comes down to just a tiny 5-second window of neglect before the surface is properly protected. Walk onto any site and you can spot the difference immediately. A properly cured slab is going to boast a richer, darker color. Run your keys across it and it's got this hard, dense finish with absolutely zero hairline cracks. But look over at a neglected pour, it's got this pale, almost dusty appearance.
That dust? It's a weak, brittle surface layer called cement latex. It's basically unreacted cement and sand that dried out way before it could form that vital glue. Plus, it'll be covered in this spider web of visible crazing cracks. I mean, good luck trying to apply any floor paint or epoxy over that. It's just going to peel right off, bringing that dusty latent layer right up with it.
Section 2. Defending the pore. Practical curing solutions. Since we know evaporation is public enemy number one, how do we actually keep that water locked in? Well, for flat surfaces like big floor slabs, the gold standard is absolutely the ponding method. Workers basically build small sand or earth dikes right around the perimeter of the slab and literally flood the surface, keeping it submerged under a continuous pool of water. It's wildly effective because it perfectly prevents any moisture loss. And as a huge bonus, it cools the concrete against that hot weather. Sure, it's pretty water intensive and takes some extra labor, but the resulting strength, totally unmatched. Now, for really massive areas where building miles of sand dikes just isn't feasible, continuous fogging or misting is a fantastic alternative. You essentially spray a very fine mist of water right over the installation. You're not trying to drown the concrete here, you just want to continuously replace that evaporating bleed water and keep the ambient humidity directly above the slab super high. This basically stops those microscopic rubber bands from ever forming. You do have to keep a close eye on it though. It requires constant supervision and consistency during those critical first few hours.
But what about the vertical challenge? I mean, how do we cure columns and beams? Gravity kind of makes building a pond on the side of a column impossible, and continuously spraying a tall shear wall is just incredibly wasteful and hard to manage. So we've got to switch up our defensive strategy.
For these vertical structures, instead of adding water, we shift to strictly trapping the moisture that's already inside the mix. We use moisture retention barriers. One way is to tightly wrap the columns in heavy plastic sheeting, which creates this neat little greenhouse effect that traps the escaping vapor. Or you can use specialized chemical curing compounds. These are membrane-forming seals that you spray right on. They dry into an invisible, impervious layer over the pores and literally lock the hydration water inside. Oh, and honestly, sometimes the best trick is simply leaving your formwork in place for an extra day or two. Actually, I highly recommend you take a screenshot of this slide right now. This info engineer matrix is essentially your exact playbook for picking the right curing method for practically any site scenario. Ponding is your most effective bet for flat slabs, even if it uses a lot of water. Spraying is great for massive areas but demands consistency. Plastic sheets are awesome for retaining moisture on beams and columns, though it makes visual inspection a bit tough. And those chemical curing compounds, absolute lifesavers for difficult to access areas. But just remember, they can impact your surface finish if you're planning to paint the concrete later. As we start to wrap up this explainer, I want this thought to really stick with you. Curing is not some optional, nice-to-have accessory to construction. It is the final, absolutely most critical step of manufacturing concrete right there on the job site. Protecting those microscopic bridges and dams from evaporating during the first few days literally dictates the safety, strength, and durability of the structure for generations to come.
So, I'll leave you with this. The next time you're out there pouring a slab, especially in the blistering heat where evaporation is just waiting to steal your structural integrity, ask yourself, are your site practices letting your concrete die of thirst, or are you giving it the cure it actually needs to stand the test of time? Think about it. Thanks for hanging out for this explainer, guys. Take these strategies back to your sites, defend your pores, and I'll catch you in the next one.